In this problem, we want to determine the minimum period for the clock signal, and also to determine if any hold time violations occur. I don't know if you do hold time violations in your section, so if you don't, then you can just ignore it, but it's not hard. So the first thing that you should know is that your minimum clock time is going to be TCQ. That's your propagation delay, and so when you want to get when you use your minimum time, you want to use the actual maximum you've got here. Because when we're saying minimum time, we're saying how much time do we need to allow for the clock. So worst case scenario. So worst case scenarios, I mean, even though it says minimum, we're actually looking for the maximum amount of time that could pass. So that'd be the propagation delay, and we'll use the big end of that, plus the amount of time to go through any gates, plus the setup time for a flip-flop. Now, for the gates, we want to look for the longest path. Again, we're looking for worst case scenario. Longest path from flip-flop input to flip-flop input. And in this instance, our longest path is right here. From D0 to D3. And so our minimum clock time is TCQ, which will be 1 nanosecond. These are all in nanoseconds. Plus our gates. Now we go through 2 OR gates. Notice that the logic gate, we say that the time for a logic gate is 1 plus 0.1 K, where K is the number of inputs. So for this 3 input gate, so a 3 input exclusive OR, that would be 1 plus 0.1 times 3, or 1.3. And for the 2 input exclusive OR, that'd be 1 plus 0.1 times 2, or 1.2. Has to go through both of those, so that's plus 2.5. Plus our setup time is 0.6. So that's 3.5 plus 0.6, or 4.1 nanoseconds, is the minimum clock time right there. Okay, now hold time violation. So for the hold time violation, that's how long that the minimum time that your signal needs to be stable before the clock edge, whereas what we just did was the minimum time it needs to be stable after oh wait, hold on. I got that backwards. Yeah, so the setup time is the minimum time it needs to be stable before the clock edge. That's why we have the setup time here in this T minimum. The hold time is the minimum time required for it to be stable after the clock edge. So in other words, you don't want it to change too fast. So in other words, for the hold time, and again, I'm not sure you need to know this for your section, but the hold time, you don't want it to change too fast. So you want to look for the shortest path. So the shortest path is going to be just going from flip-flop to flip-flop, from D3 to D2 or D2 to D1, not going through any gates at all. So if you don't go through any gates at all, then the amount of time that takes would be the minimum time for a propagation delay. So again, we're looking for worst case scenario, but worst case on the smallest end. So that would be, you're going to have the propagation delay, so that'll be 0.8 nanoseconds. And there's nothing else to add in there. So we want to see, is that greater than the hold time? And if that's greater than the hold time, then you're okay. And 0.8 nanoseconds is greater than the hold time, which is 0.4, so there are no hold time violations.